December 2021, and an Ariane 5 lifts off from Kourou carrying NASA's James Webb Space Telescope. It is the most complex instrument to be flown, yet its design owes much to its famous predecessors, both in terms of engineering and in discoveries that changed the way we understand the universe. The new space telescope was headed for the second Earth-Sun Lagrange point, 1.5 million kilometers beyond the Earth's dark side. During its 4-week journey to L2, the telescope unfolded in gradual steps. Soon after separation from the rocket's upper stage, the solar panel was unfurled and the spacecraft's batteries began charging. 2.5 days into its journey, the fore and aft sunshield pallets were lowered, and the mirror assembly extended 2 meters above the body of the spacecraft. Then the 4 layers of Captain E that make up the sunshield were unfurled and tensioned. This allowed the observing section of the spacecraft to cool down to minus 233 degrees Celsius, 40 degrees Kelvin. This is important. The Webb telescope is optimized for near and mid-infrared light, which cannot penetrate the Earth's atmosphere. It is designed to see stars and galaxies forming in the early universe. Any warmth in the telescope would inhibit its vision in the red end of the spectrum. Finally, the secondary mirror and the 2 wings of the primary mirror swung into place. In the San Gabriel Mountains northeast of Los Angeles is the Mount Wilson Observatory. It was with the 100-inch Hooker telescope that Edwin Hubble proved that the universe extends beyond our own galaxy and that the universe itself is expanding. But such large ground-based instruments were reaching size limits.
5, 4, 3, 2, 1, and liftoff of the Space Shuttle Discovery with the Hubble Space Telescope.
In 1990, a space telescope that was named in honor of Edwin Hubble was launched. The orbiting telescope refined estimates of the age of the universe at 13.7 billion years and its rate of expansion. Hubble established the prevalence of black holes, especially as the center points of galaxies. The telescope's extreme sensitivity led to the discovery of GN-Z11, the most distant known galaxy. The light from very distant objects is shifted toward the red end of the spectrum. GN-Z11 was at the limits of Hubble's sensitivity in the infrared. In 2003, NASA launched a telescope sensitive into the far infrared. It became known as the Spitzer Space Telescope. It was the first spacecraft to be placed in an Earth-trailing orbit around the Sun. Spitzer carried 360 liters of liquid helium to cool its observational components. To operate effectively, it needed to be kept at 5 degrees Kelvin, and its designers knew that its sensitivity in the far infrared would die when the helium coolant ran out. By comparison with Hubble, Spitzer's primary mirror was small, just 85 centimeters across. Although this limited its sensitivity, its observations deep into the low end of the spectrum gave researchers a completely new view of familiar objects. The Helix Nebula in the constellation Aquarius is the remnant of a mid-sized star that has exploded, expelling its outer layers of gas and dust that glow under the influence of the stellar remains. Here, it's viewed by Hubble in the visible spectrum. In the far infrared from Spitzer, areas of the opaque dust and gas are now transparent. At these wavelengths, vast areas of the sky can now be penetrated. Even while Hubble was still being built, astronomers had been planning a next-generation telescope to replace it. The trend in telescope building has always been toward bigger instruments that have greater light-gathering power and that can see in greater detail. But Hubble's 2.4-meter mirror was about as big as the current generation of launchers could carry to orbit. Terrestrial telescopes have much larger mirrors, but their designers realized that huge slabs of glass would sag and distort. They came up with radically new solutions. At the European Southern Observatory at Paranal in Chile, 4 identical telescopes with 4 smaller auxiliary telescopes are collectively known as the Very Large Telescope, or VLT. They can be linked together via interferometry. Each of the large telescopes has an 8.2-meter mirror, which is only 17.5 centimeters thick. The VLT takes advantage of the thin mirror's ability to flex and distort. Beneath each mirror, 150 axial force actuators dynamically control the mirror's shape in a technique known as active optics. Other new generation telescopes had solved the large mirror problem in a different way. A group of hexagonal mirrors could be made to function as a much larger mirror by making use of actuators to align them. Hawaii's twin Keck telescopes were the first major instruments to use this technology. Each telescope has a 10-meter primary mirror made of 36 segments. By 2002, NASA had settled on a design for what had been known as the Next Generation Space Telescope. It was an amalgam of lessons learned from orbiting and terrestrial instruments, and its primary mirror, made up of 18 hexagonal submirrors, measured 6.5 meters across. It was a huge advance on Hubble, whose mirror is 2.4 meters in diameter, with very limited sensitivity into the infrared end of the spectrum. And while it occupied more space than Hubble, its segmented mirror allowed it to fold up into a small configuration for launch. NASA's European partners would provide launch services on an Ariane 5. In 2002, the telescope was renamed the James Webb Space Telescope. James Webb was NASA's administrator during the Apollo program. He was instrumental in giving the agency a science focus, establishing the Mariner and Pioneer programs that began exploration of the solar system. The James Webb Space Telescope is the beginning of a new age in astrophysics. With it, astronomers will be able to see light that has been traveling since the earliest years of the universe, providing answers about the formation of the first galaxies. To achieve such ambitious goals required the new telescope to incorporate at least 10 completely new technologies.
In order to discover the things that we have never seen before, we need the best equipment we can possibly have. So the telescope that we're building has no substitute. There's no other way to get at this scientific discoveries that it'll make. What it'll really find that we don't know? Well, I don't know. It's a mystery. So we build these telescopes with great confidence that we will open up new mysteries of the universe whenever we build them. It's happened time after time after time for centuries.
The JWST's primary role is as an infrared telescope. With its very large mirror and its enhanced sensitivity at the low end of the spectrum, astronomers are hoping to see light generated 13 billion years ago, but the telescope can only achieve this if it functions at very low temperatures. This is why it's positioned at the L2 point, 1.5 million kilometers beyond heat radiated from the warm Earth. Here, its large sun shield will protect it from solar radiation, allowing its observing side to cool to 50 degrees Kelvin. Even so, its mid-infrared instrument will need its own cryogenic refrigerator to cool it further to just 7 degrees Kelvin. The extreme cold environment in which the JWST must function meant that all its components had to be tested at cryogenic temperatures. From the beginning, engineers knew that building the mirrors for the James Webb Space Telescope would take them into uncharted territory. They had decided to make them from beryllium, a rare metal that behaves well at low temperatures. It is lighter than aluminum, yet stronger than steel. A number of hexagonal blanks were brought to a uniform thickness. Then the rear side was hollowed out to reduce weight, leaving a rib structure that maintains stiffness. Designers knew the precision curve would change when the mirrors were brought to their cryogenic operating temperatures, so the grinding and polishing process was carried out in 2 stages. After their initial polishing, the first batch of mirror segments was sent to the Marshall Space Flight Center for testing in the X-ray and cryogenic facility. All air was removed from the chamber and the mirrors chilled to 40 degrees Kelvin. Testing of the individual segments resulted in a heat map used back at the polishing laboratory to refine the segment's curve so that it will be accurate at its deep space temperature. The finished hexagons must then be individually cleaned before getting a final surface layer. Less than 3 grams of pure gold covered the face of the segment via vacuum deposition, a process that took about an hour. The final gold layer, less than 1/1000th the thickness of a human hair, provides maximum infrared reflectivity. Several other mirrors, not part of the large primary array, are crucial to the telescope's functioning. The convex secondary mirror sits at the focus of the primary array and directs light down to the tertiary mirror inside the shielded structure at the center of the large array. Finally, an optically flat fine steering mirror, also within the central structure, directs light to the instruments. Before the finished mirrors could be integrated with the other parts of the telescope, there was one final test. A 3-axis sine vibration test would verify that the mirror could survive the rigors of launch. Short bursts of vibration at varying frequencies duplicated the environment a satellite experiences during the early phases of flight on an Ariane 5. It had taken 11 years for all the mirrors, plus spares, to be completed. Another major challenge was the folding backplane structure that would support the mirrors and most of the scientific hardware. A simplified Pathfinder unit was constructed first. Every part of the fabrication, handling, and testing would be practiced on this item before the final flight backplane became available. In January 2007, 9 of the 10 pioneering technologies being developed for the JWST passed a critical design review. The cryogenic cooler required by the mid-infrared instrument passed 3 months later, but the project was behind schedule and over budget. Around this time, the public became dimly aware of the James Webb Space Telescope because its famed predecessor, Hubble, was in grave trouble. It was feared that space-based observations would go black until the JWST was launched.
Columbia, Houston, com check.
After the Columbia broke up during re-entry with the loss of all crew, the space shuttle was only permitted to fly to the International Space Station. Hubble, designed to be serviced on orbit, was no longer within reach of the shuttle. The aging telescope's much-needed final upgrade had been canceled. Public pressure and intense lobbying from Congress caused the NASA Administrator Michael Griffin to reconsider.
We are going to add a shuttle servicing mission to the Hubble Space Telescope to the shuttle's manifest to be flown before it retires.
It was a popular decision, but it took a while to happen. As the Space Shuttle Atlantis was being prepared for launch in September 2008, the Hubble's Science Instrument Command and Data Handling Unit failed. So important was this unit that the flight was suspended for 8 months while a replacement unit was prepared and mission specialists could be trained for the extra task.
T-minus 10, 9, 8, 7, 6, 4, 3, 2, 1, and liftoff of Space Shuttle Atlantis. A final visit to enhance the vision of Hubble into the deepest grandeur of our universe.
Atlantis finally lifted off in May 2009. The repair mission was a success, but it would be the last. Any subsequent breakdowns could mean that Hubble would go dark. This added pressure to the team building the JWST. Deep in space, there could be no missions to repair it, so this extremely complex new telescope had to be flawless. Soon, funds from other NASA projects were being diverted to keep the observatory afloat, and James Webb was being referred to as the telescope that ate astronomy. Work continued on the telescope, and while there was relief among the James Webb team at NASA, political scrutiny of the way in which the space agency managed such elaborate one-off projects became intense. In July 2011, the U.S. House of Representatives Appropriations Committee on Commerce, Justice, and Science moved to cut NASA funding, effectively killing off the JWST. The committee issued a statement saying the program is billions of dollars over budget and plagued by poor management. Ultimately, the move was blocked, but an $8 billion cost cap was set. So much had already been invested in the project, and politicians were reminded that the very popular Hubble had met similar resistance during its development.
It's taking longer than we thought to build this amazing telescope, partly because we never built one before like it. It is enormous. The sunshade that we have to build is as big as a tennis court. It has to be folded up really small, so when we get it up there, it can unfold properly in outer space. We have to rehearse and practice, and we have to find those little mistakes that people always make and fix them. So it's difficult, but it's worth it.
While the astronomers and engineers were happy that the James Webb project had survived, this would not be the last political obstacle that NASA and its contractors would face. In the 1960s, NASA had constructed Chamber A, a thermal vacuum chamber big enough to hold the Apollo Command and Service Module. This is where the optical telescope element of the Webb was tested, but it needed a serious upgrade before that could happen. The area outside the big door was made into a clean room, and contamination from lubricants present in the chamber was expunged. The refrigeration unit was replaced with a new system that could chill to 35 degrees Kelvin. When the James Webb Space Telescope left the Earth's orbit, its solar panel and its dish antenna were rapidly deployed. This gave it power to function and the ability to communicate with the ground. By the end of the 6th day, Webb's sunshield was fully unfurled, allowing the shaded side of the craft to begin cooling. In the vacuum of space, plastics, lubricants, epoxies, and other materials begin to outgas. This release of constituent molecules can settle on and degrade optical surfaces. Outgassing diminishes rapidly as the craft cools, and the timing of the telescope's deployment was largely based upon results observed in Chamber A at the Johnson Space Center. Early in 2015, Chamber A had been fitted with optical test equipment ready for the first exercises in aligning several mirror segments under simulated deep space conditions. 2 separate series of optical pathfinder tests were made with this configuration. A third thermal test was conducted on the Pathfinder, fitted with 2 spare mirrors and a set of dummy aluminum blanks to duplicate the thermal mass of the flight telescope. These tests each lasted months. Toward the end of 2015, almost all the Webb spacecraft's components existed as separate pieces in different locations. With the arrival of the fully tested backplane structure at NASA Goddard's giant clean room in Greenbelt, Maryland, final assembly of the optical portion could begin. The sunshield and propulsion elements were being assembled at Northrop Grumman's facility at Redondo Beach in California. At NASA Goddard, a large jig had been constructed in the clean room to cradle the mirror array as it was being integrated. The backplane was one of the new technologies that had to prove itself before final work on the telescope could begin. It had to be light, strong, and stable to nanometer scale at 50 degrees Kelvin. The lightweight mirrors were another new technology that went through exhaustive verification before final assembly. While each mirror segment has been delicately machined down to just 20 kilograms, an actuator fitted to its back doubles that weight. A centrally located motor attached to rods stretching to the corners of the mirror can change the curvature of the individual segment, while 6 more motors can adjust the tilt of the segment along 3 axes. Once in space, and after the complete structure had been deployed, engineers waited approximately 40 days until the telescope had cooled to its operational temperature. They then began aligning or phasing the telescope's primary mirror segments via the actuators. The segments can be moved in increments approaching 1/1000th of a meter. After pointing the JWST at a bright star, its near-infrared camera was used to ascertain how much each mirror segment needed to be shifted so that the individual parts can function together as a whole mirror. After the phasing of the primary mirror segments, the small secondary mirror was aligned, then the tertiary, then the 4 science instruments. Fine-tuning using the near-infrared spectrograph can be done with exquisite accuracy. The initial alignment took several months, and when the telescope is making observations, it will be checked regularly. For a telescope to function with such precision in deep space, its assembly had to be carried out with equal precision. A robotic arm, known as the primary mirror alignment and integration fixture, can position each segment with an accuracy measured in fractions of a millimeter. A team working below the backplane used a laser to judge the exact position of each mirror segment before fixing it in place and then connecting the actuator's wiring. The Integrated Science Instrument Module, or ISIM, houses the Webb's 4 science instruments and the fine guidance sensor. Before it could be united with the telescope, it had to be subjected to the extreme stresses it would experience during launch, so it was brought to NASA Goddard's giant centrifuge. During the test, it was exposed to forces 7 times greater than gravitation here on Earth. The lightweight structure passed with flying colors and was fitted with its cameras, spectrographs, and associated electronics. Now, the whole unit needed testing. Just like every other piece of the Webb Observatory, the ISIM had to be subjected to extremes of cold as well as juddering vibrations. Before it could be united with the mirror array, the instrument module went through 3 separate sessions in Goddard's Space Environment Simulator. This replicates the same cold vacuum environment as Chamber A at the Johnson Space Center, but it is smaller. A helium shroud has been added to duplicate the extreme cold at which Webb must function. During the first test, there were problems. The layered semiconductors that make up the infrared detectors expanded and cracked with the extreme temperatures. NASA and its consortium partners had to redesign these crucial components rapidly or risk adding yet more delay to the project. Another problem arose during the shake test of the instrument module. One of the new technologies developed for the Webb is the micro-shutter assembly. It's an array of 250,000 small doors, each about twice the diameter of a human hair. Used in conjunction with the spectrometer, the microshutters allow researchers to sample individually selected astronomical targets. Each tiny door can be opened magnetically, but the early version of the microshutter array did not survive the shake tests and also had to be redesigned. The ISIM is the brain of the telescope, converting light from the mirrors into data that can be transmitted back to Earth. It was delicately positioned behind the primary mirror array, and by November 2016, the telescope structure was complete. It had taken shape in NASA Goddard's clean room, and while a special traveling case had been built for it, the telescope's first trip outside the clean room would be just down the corridor to the vibration testing facility to see how it behaved under launch conditions. It was protected from contaminants by a plastic tent. The Webb telescope, tent and all, was lifted onto a shake table and fitted with monitors. Tests began in December 2016, but anomalous sensor readings led to an automatic shutdown. It took experts a while to understand that small motions in the launch restraint mechanisms for one of the folded mirror wings had happened because the restraint latch had not been closed properly. It was a valuable lesson for the team, and testing procedures were modified, coming to a successful conclusion the following month. The next test required the Webb telescope to make its first journey. To do this, a specialist group of engineers packed the telescope in its launch configuration into a plastic shroud to provide an added layer of protection. This, in turn, was encased in the custom-built STARS container. STARS is one of those peculiar acronyms of which NASA is so fond. It stands for Space Telescope Transporter for Air, Road, and Sea. In May 2017, the telescope was on its way to Houston, Texas, and NASA's Johnson Space Center for testing in Chamber A. At the Johnson Space Center, the STARS container was wheeled into the newly created clean room adjacent to Chamber A. While this clean room is big, there is only just enough room to unpack the telescope and to configure it for the cryogenic testing. The telescope had to be mounted upon a large steel platform which slid upon rails. Also mounted on the platform were the various pieces of the telescope's test equipment. Though this is the biggest thermal vacuum chamber in the world, there was just enough room for the deployed telescope. Once inside the chamber, it was suspended from 6 steel rods that isolate the unit from vibration caused by refrigeration tubing and vacuum pumps. The internal helium shroud was another modification to Chamber A. By passing liquid helium through the tubing within the shroud, the JWST can be cooled to the temperatures it will experience in space. It was July 2017, and it had taken the engineers more than 2 months to prepare the telescope for these tests. A team from NASA Johnson operated the chamber while engineers from NASA Goddard conducted the tests. It took close to a week to evacuate the chamber and a further 30 days to bring everything inside down to 40 degrees Kelvin. The two main areas of interest were the ability of the individual segments to be aligned and perform as a single giant mirror, and for the telescope's 4 instruments to read the images that they were receiving. Everything functioned as intended, and by late September 2017, the team began allowing the telescope to return to room temperature. After 93 days, the door was reopened and the Webb telescope began preparation for its next journey. At the Northrop Grumman facility at Redondo Beach, just outside Los Angeles, the spacecraft element of the observatory had been taking shape independently of the telescope element, but problems with the sunshield had led to delays. Rips in the capstan layers and difficulties with the cables designed to tension the shield needed more time to resolve. Managers had decided to delay bringing the telescope element to California for final integration, while technicians at Redondo Beach fixed the problem.
Hold that. Just lost the cable.
The telescope had been scheduled for a clean at Northrop Grumman, but this now happened at NASA Johnson, where there was more space for the painstaking examination of the individual segments. The delays had eaten into the reserve schedule, and the launch date had been postponed several more times, with planners settling for March 2021. In February 2018, the telescope element arrived at the Redondo Beach facility. This was the first time that all pieces of the James Webb Observatory had been in the same room. The remaining work involved the uniting of the telescope element with the spacecraft element, followed by yet more testing. However, there would be no more testing at low temperatures. With the two halves of the observatory required to function in such different thermal environments, this was not possible. The sunshield continued giving problems. To avoid the risk of snags, a decision was made just to tighten the locking nuts on the fasteners till they were flush with their bolts. As work proceeded, NASA set up an independent review board to assess progress on the Webb telescope and its ballooning cost. The board was sympathetic to the problems associated with building a one-off instrument of such complexity, but they were critical of human error that resulted in costly delays. The wrong solvent was used to clean spacecraft propulsion valves, and improper test wiring meant excess voltage damaged several transducers. The cost-plus nature of the agreement signed with contractor Northrop Grumman saw no disincentive for these mistakes, which could be seen as a conflict of interest. But work on the James Webb Space Telescope was so advanced, and so much money had already been committed, that there was no danger of Congress withholding funding for the remainder of the work. The James Webb Space Telescope was folded into its launch configuration, and then several practice deployments were executed. It is impossible to duplicate the zero-gravity environment present when these deployments are made in space, so support cables and counterbalances were connected to the moving parts to approximate weightlessness. The sunshield was deployed, and it appeared to be working well. But then there was the inevitable testing. The craft was folded up and cased in another plastic tent to protect against contamination, and moved to Northrop Grumman's Shake facility. Now, the complete structure was subjected to the heavy vibration it would experience during launch. Back in the clean room, technicians discovered that dozens of bolts had shaken loose, and it took the team 3 weeks to locate each part, some lodged deep within the telescope structure. This incident was also included in the report of the Independent Review Board. It concluded that NASA had a culture of optimism, and that conforming to a budget was not how the space agency judged success. Projects like Webb tend to starve other programs of resources. The Nancy Roman Telescope is a planned wide-field, high-definition survey telescope able to complement Webb's observations. Components are being fabricated, but the telescope exists only as an animation. The problem of fasteners parting company with the sun shield was resolved by tightening 570 nuts to a new torque specification, and was verified with more shake tests. This had not been a serious delay, but with the onset of the coronavirus pandemic in 2020, the launch date slipped again to no earlier than October 31st, 2021. Now, a new issue arose. The Ariane 5 that launches the JWST to orbit had been returning data about excessive vibration happening when the fairing was jettisoned. While the two launches that showed this data successfully deployed their payloads, NASA was worried what this might do to the Webb's folded layers of shielding. A fairing is fitted with valves that gradually release air as the rocket rises through the atmosphere, but it seemed that there was residual pressure in the payload space when the fairing was ejected. Engineers building the Webb thought that air trapped within the layers could damage the shield with the sudden drop in pressure. Changes were made to the fairing, and there were 2 Ariane 5 launches before Webb was due to fly that allowed technicians to be certain that the new fairing was behaving properly. The final major testing happened over 17 consecutive days. The comprehensive systems test had all electrical systems working as if the telescope was operational. More than 1,000 scripts, or sequences of instructions, were executed, and software amendments were sent and verified. The telescope was even connected to the Deep Space Network, as it will be when it's in space. While the clean room in California looked quiet, staff at the Space Telescope Science Institute in Baltimore were busy making certain that all systems were working harmoniously. The telescope builders were now confident that the largest, most complex space telescope yet made was functioning as expected, but there remained doubters who felt its complexity was a problem. Thomas Young, chair of the Independent Review Board, cited 307 single-point failure items. A malfunction in any one would doom the mission. By contrast, the recent Mars rovers had 75 single-point failure items, yet they were still seen as high-risk missions. Both Curiosity and Perseverance landed successfully and are fully functional to this day. The board made 32 recommendations for actions that NASA could take to minimize failure, and the agency accepted all of them. When the final testing of the telescope had been completed, it was prepared for shipping to Kourou. A shroud of secrecy was drawn around the schedule for transporting the JWST. Mission planners worried that such an expensive piece of hardware might attract hostile intent. It was only after the event that pictures of its passage through Los Angeles were released. Inside its special container, the telescope had been fitted with a series of shock detectors to determine whether, in transit, it had received inadvertent jolting. Webb, complete with the truck that hauled it, was loaded into the MN Colibri for its final journey to the European Space Agency's launch site at Kourou in French Guiana. The shallow Kourou River at Pariacabo had been specially dredged, and the ship arrived at high tide to ensure there were no surprises. The Webb telescope is the single most valuable payload that the Ariane 5 will launch, and everyone at the space complex was aware of the significance of this mission. Several months earlier, components for the Webb's launcher had also arrived by ship to cover the last 3 kilometers of the journey behind a similar truck. Roughly 55 days had been allowed to prepare the telescope and its launcher. Once back inside a clean room, the telescope was unboxed and brought to the vertical. it was mated to the launch vehicle adapter that ultimately connects to the Ariane's upper stage. A simple tension band maintains the connection till it is in space and ready to be set loose. But the band malfunctioned, sending a jolt through the telescope. This delayed the launch by 4 days while technicians looked for damage. Meanwhile, various parts of the Ariane 5 were converging on the Ariane assembly facility. While the rocket is essentially a standard Ariane 5, the upper stage has been modified to carry out a gradual rolling maneuver to protect Webb's folded mirrors from excessive solar radiation. After its preparation, Webb was moved to a separate facility for fueling. The telescope needs its own propulsion system to adjust its orbit around the second Sun-Earth Lagrangian point and to facilitate accurate targeting. Fueling is a precision exercise, as the hydrazine and nitrogen tetroxide propellants are extremely toxic. Next, the telescope was moved via a mobile clean room to be mated with the Ariane 5. While the James Webb Space Telescope weighs less than Hubble, it occupies more space. Mechanical handling of the telescope called for greater delicacy as clearances were narrow. Connection to the upper stage was straightforward. The launch fairing was now fitted with 24 pressure release valves to make certain that early problems with residual pressure when the fairing is jettisoned had been eliminated. Laser guide devices had been introduced for the encapsulation procedure to monitor the fine clearances. A minor communication problem between the telescope and the rocket delayed the launch by several more days. But finally, on Christmas morning in 2021, the countdown was nearing completion.
And we have to start. And liftoff.
Almost immediately, the telescope advanced understanding of the early universe and the nature of exoplanets. Much more is expected.